Hello, my name is Björn Askeland. This is my fifth video about Riemann's hypothesis. This is a documentation of the first 269 convergent Riemann zeros. I will in this video explain how I do these calculations. Saying that the zeta sum is convergent inside Riemann strip is like swearing in church. I have since 2008 claimed that this is true, and you can see the proof here on YouTube in video 1. The convergent zero means that the zeta sum formula can be factorized. And according to established theory, that is impossible. Inside Riemann's critical strip, the zeta sum formula is considered to be divergent. I have proved that there is general divergence inside Riemann's critical strip, but the exceptions are Riemann zeros, which are convergent zeros. Riemann zeros are hidden in an ocean of infinity as convergent zeros. So when I submit my work to a journal, my paper will be rejected because it breaks with established theory. But established theory must be wrong. It's correct that all Riemann zeros lie on the critical line, but they are not just analytic zeros, they are also zeros of the zeta sum formula. The condition which explains that Riemann's functional equation only can have zeros on the critical line also makes it possible to calculate convergent zeros. Convergent zeros are therefore a direct consequence of my proof. Look at these very complicated curves. How can it be possible to calculate 269 zeros based on a condition from a mathematical proof, and then say, this must be incorrect since someone made a definition that this cannot be done? But I have made the calculations. You see 269 convergent zeros in both plots, as pi radians phase shifts in the upper plot, and as green spikes in the lower plot. Let me explain the plots for you. The lower plot shows spikes for every Riemann zero between b equals 12 and b equals 500. The green plot is the derivative of the red plot. I explained the red plot in video 4. But let us review the upper plot. In video 4 I showed that the phase of the Euler product swings around Riemann's blue analytic continuation. I also showed that it's possible to solve Askeland's condition and recalculate the Euler phase diagram only for the solution of the equation. Then I end up on Riemann's curve. Let me show you a practical example. I have zoomed in to the first zero. When I use all the b values on the imaginary axis, the Euler phase looks like this. In this example, the length of the zeta function is 9973. Then you have to enter 9973 into Askeland's condition. Then solve the equation with n equals 9973. And solve for all natural numbers of k. And then sort out the b values of the solution around Riemann's first zero. These b values are the values where Askeland's condition is satisfied near Riemann's first zero. For these b values, a large sum is removed from the zeta sum. Next step is to enter these values into the Euler phase formula. Then I land on Riemann's analytic continuation, but only for discrete values. And zoomed out, it looks like this. And if I choose to use higher values for n, I always land on Riemann's analytic curve. It's amazing that the sum formula gives the same zeros even though the length of the zeta function is increased in small steps from 10,000 to 10 millions. These are the first 10 convergent zeros of the zeta sum formula calculated for different values of L. And when max imaginary value is 500, the discrete phase diagram looks like this in the upper plot. The lower plot is simply calculated as the derivative of the phase. The derivative is the difference between two consecutive phases divided by the difference in b-values between the two phases. The brown line is a threshold line in order just to detect phase shifts as large as pi radians. Then I detect all 269 zeros within imaginary path 500. You have just seen the calculation of 269 convergent Riemann zeros. Riemann zeta sum can be factorized with these zeros. These three formulas we use to calculate the convergent zeros. Thank you for watching.